Welcome to Module 5, Unit 3, Auto Contrast Adjustment. In this unit, we'll explore how automatic contrast enhancement works, why it's important in image analysis, and how we can implement it efficiently in practice. By the end of this lesson, you'll understand both the basic and modified approaches to auto contrast and see how they can dramatically improve the quality of an image. Contrast is the difference in brightness, also known as luminance, or in color that makes objects distinguishable. In this example, the text on the left and the right is identical. The letters have exactly the same intensity level. At first, both sides use a white background. On the left, the dark gray text at the top is easier to read than the lighter gray text at the bottom. Now, when the background on the right changes to black, notice what happens. The top text becomes harder to see, while the lighter text at the bottom stands out much more clearly. So even though the text color never changes, the contrast with the background determines how easy it is to read. On this slide, we are comparing three versions of the same image, each with a different level of contrast. At the top, you see the low-contrast version on the left, the mid-contrast version in the middle, and the high-contrast version on the right. Now, look at the bottom row, where each image has a corresponding histogram. A histogram shows how pixel intensities are distributed from dark to bright. At first glance, the overall shapes look somewhat similar, but the range of values being used makes all the difference. In the low-contrast image, most of the pixels are squeezed into a narrow range in the middle of the spectrum. That means only a small portion of the available intensity levels is being used, which makes the image look flat and lacking detail. In the mid-contrast image, the pixel values spread out more widely, reaching into darker and lighter regions. The image becomes clearer, with stronger separation between tones. In the high-contrast image, the histogram stretches across almost the entire spectrum, from very dark to very bright. This full use of the intensity range produces the sharpest image, with details that stand out much more strongly. So the key idea is this. A high-contrast image tries to make full use of the available intensity spectrum, while a low-contrast image is restricted to just a small portion of it. Automatic contrast adjustment, often called auto contrast, is a process that enhances an image by making full use of the available intensity range. The idea is simple. Instead of leaving parts of the spectrum unused, we stretch the pixel values so that the entire range from dark to bright is covered. Let's look at the histogram on the left. This represents a low-contrast image. Notice the empty regions marked by the red boxes. These sections of the intensity scale, very dark pixels on the left and very bright pixels on the right, are not being used at all. Because the pixel values are clustered in the middle, the image looks flat and dull. Now, if we take this distribution and stretch it outward, something interesting happens. The lowest pixel value is remapped to pure black, and the highest pixel value is remapped to pure white. The intermediate values are then spread proportionally between these two extremes. That stretching process is illustrated here with the green and blue arrows. After the adjustment, as shown in the histogram on the right, the entire intensity spectrum is now utilized. The image that results has a stronger separation between dark and bright regions, producing much clearer details and a more natural appearance. So the key takeaway is this. Auto contrast works by redistributing the pixel intensities so that all available levels, from the darkest to the brightest, are put to use. To achieve auto-contrast, we use a mapping function that converts old pixel values into new ones. On the red line at the top, we have the original low contrast range. Here, VD is the darkest pixel value, VB is the brightest, and VI is any pixel value in between. On the green line at the bottom, we see the enhanced range. The lowest intensity, called VL, is set to 0, and the highest intensity, called VH, is set to 255. After adjustment, the pixel VI is mapped to a new value we call VN. You can think of the red line as an elastic band stretched between VD and VB. When we pull it outward to cover the full range from VL to VH, every point in the middle is stretched proportionally. So the original VI in red becomes VN in green. The formula at the bottom captures this proportional relationship. It makes sure that the spacing between pixel values in the original range is preserved when we stretch them into the new range. That is how we calculate the adjusted pixel value VN. According to the mapping formula we learned, we can now design a MATLAB function to perform auto-contrast. Here you see the function template named auto-contrast. It takes a low-contrast gray level image, called IMG, as its input and produces an enhanced image, called IME, as its output. To make full use of the gray level spectrum, we first define the minimum output intensity, VL, as 0, and the maximum output intensity, VH, as 255. Next, we find the darkest and brightest pixel values in the input image. These are VD for the minimum intensity and VB for the maximum intensity. Once we have VD and VB, we can apply the mapping formula. This formula transforms every pixel value VI in the original image into a new value VN in the enhanced image. The result is an image where the entire intensity range is fully utilized, giving us stronger contrast. To perform auto-contrast, we first need to know the smallest and largest pixel values in the image. These are VD, the minimum intensity, and VB, the maximum intensity. In MATLAB, we can find them using the functions called min and max. However, there is one important detail. When these functions are applied directly to a two-dimensional image matrix, they return the minimum or maximum for each column, not for the entire image. To correctly find the overall minimum and maximum values, we need to convert the image matrix into a single column vector. In MATLAB, this is done by writing IMG : inside the parentheses. For example, min of IMG : gives the smallest pixel value in the whole image, and max of IMG : gives the largest pixel value. Now we'll turn the mapping equation into a single MATLAB expression. The idea is, take each original value VI, shift it by subtracting VD and adding 1, then scale it by the constant ratio, VH minus VL plus 1, divided by VB minus VD plus 1, and finally subtract 1. This preserves the relative spacing while expanding to the full range. In MATLAB, compute this in one step using element-wise multiplication. Vn equals Vi minus Vd plus 1, element-wise times the scale factor, Vh minus Vl plus 1, divided by Vb minus Vd plus 1, then minus 1. Use dot star, so the operation applies to every pixel in the array. This vectorized form is fast and avoids loops. This slide shows the complete MATLAB implementation of auto-contrast. First, we convert IMG to double, so that all calculations are accurate and precise. Then we define the output intensity range, setting VL to 0 and VH to 255. We also determine the darkest and brightest pixel values in the original image, which are stored as VD and VB. Using these values, we map every pixel in IMG to a new value across the full intensity range. Finally, because we want the enhanced result to be a proper grayscale image, we convert IME back to UINT8. This ensures that the output image can be displayed correctly in MATLAB as an enhanced grayscale image. The basic auto-contrast method works well in many cases, but it has one important limitation. It is very sensitive to extreme pixel values. For example, if a single pixel in the image has an intensity of 0 and another pixel has an intensity of 255, the algorithm will treat those as the minimum and maximum. As a result, no stretching will occur, and the image contrast will not improve at all. To overcome this issue, we modify the method. Instead of using the absolute minimum and maximum pixel values, we look at the distribution of all pixels. Then we ignore the bottom 0.5% and the top 0.5%. The pixel value at the bottom threshold becomes the new minimum, and the value at the top threshold becomes the new maximum. By trimming just a tiny fraction of the pixels at both ends, we prevent outliers from controlling the entire adjustment. This ensures that the majority of the image benefits from the contrast enhancement, while still covering the full intensity spectrum in a more reliable way. Here we revise the auto-contrast function to make it more robust. The new version is called Modified Auto-Contrast. It takes a low-contrast grayscale image, spelled IMG, as input and produces an enhanced image, spelled IME, as output. We still define the output range as before, setting VL to 0 and VH to 255. But instead of using the absolute minimum and maximum from the image, we replace them with threshold values. Specifically, we will look up the pixel intensity at the bottom 0.5% of the distribution as the new VD, and the intensity at the top 0.5% as the new VB. Once we obtain these values, the formula we used earlier can be applied in the same way. This maps every pixel intensity, VI from the original image, to a new intensity, VN in the enhanced image. By trimming off just 0.5% at both ends, the modified function avoids being dominated by a few extreme pixels, giving us a more reliable contrast enhancement. In order to find the pixel intensity at the bottom 0.5%, and the top 0.5%, we first need to sort all pixel values in the image. In MATLAB, the function called sort can be used to arrange values in order. But there is one important detail. When sort is applied directly to a two-dimensional image matrix, it sorts each column individually, not the entire matrix. To sort all pixels together, we must first reshape the image into a single column vector using IMG:. Then we apply sort to that vector. The result is one long ascending list of all pixel intensities in the image, which we can use to locate the threshold values for modified auto-contrast. Once all pixel values are sorted in ascending order, we can identify the intensity at the bottom, 0.5%, and at the top, 0.5% of the distribution. To do this, we first need the total number of pixels in the image. In MATLAB, we find this using the function called numal on IMG. This gives us the variable p, which represents the total pixel count. The index for the bottom threshold is calculated as p times 0.5%, rounded to the nearest integer. This index points to the pixel intensity at the bottom 0.5% of the sorted list, which we use as the new VD. Similarly, the index for the top threshold is calculated as p times 99.5%, which comes from 1 minus 0.5%. After rounding, this index points to the pixel intensity at the top 0.5% of the sorted list, which we use as the new VB. By retrieving these two values, we avoid being misled by outliers at the extreme ends of the image. Now we can put everything together in the complete function called modified autocontrast. First, to avoid losing precision in calculations, we convert the input image IMG from UINT8 to double, and we store it as VI. We also compute P, the total number of pixels in the image, using the function called numal on IMG. Next, we define the output intensity range as before. VL equals 0 and VH equals 255. Then we sort all pixel values in ascending order and store them in a list called L. From this list, we take the value at p times 0.5% as the new VD, and the value at p times 99.5% as the new VB. These represent the adjusted minimum and maximum thresholds. Finally, we use a matrix operation to map every pixel intensity in VI to its new value Vn, which is stored in IME. At the end, we convert IME back to UINT8, so that MATLAB recognizes it as a proper grayscale image. This complete function implements the modified autocontrast algorithm, which avoids being misled by extreme pixel values and produces a more reliable contrast enhancement. Now, let's test the effectiveness of the modified autocontrast function. First, we load a low-contrast image, shown on the left side of the figure. This is stored as IMG. We then pass this image into the function modified autocontrast. The function processes the image, adjusts the pixel values using the 0.5% thresholds, and returns the enhanced image, stored as IME. On the right side of the figure, you can see the result. The enhanced image has stronger separation between light and dark regions, making details much easier to see compared to the original low-contrast version. This demonstrates how the modified autocontrast algorithm successfully improves image quality by stretching the pixel intensities while ignoring extreme outliers. In this unit, we learned how autocontrast works by stretching pixel values to make full use of the intensity spectrum. We saw how the basic method can fail when extreme outliers dominate, and how the modified approach solves this problem by ignoring the top and bottom 0.5% of pixels. Through MATLAB implementation, we practiced converting images to double, finding threshold values, and applying matrix operations for efficient mapping. Finally, we confirmed the improvement by comparing a low-contrast image with its enhanced version. The key takeaway is that autocontrast, especially the modified version, is a powerful yet simple technique for improving image clarity and preparing images for further analysis.